Check, 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 check. Check, check, hey, hey.
Check, check, check.
Wait, does it? Yeah.
There you go.
I'll introduce you. Thank you so much.
You're welcome. You're gonna run. Oh, no worries.
I am.
Okay. So you know what the button is for, how to use it now?
Well, yeah, but
Okay.
no, it's not obvious.
Understood, but it was my interest just to make it it's like it goes public. So
Okay.
the video that they're going to give you as the decision.
Sorry, everyone's frustrated. Very good. Okay. Wait, is this on? Yes. Hi, everybody. Good morning and welcome to the last day of SCaLE.
If they are not using it, they're holding it wrong and all the stuff. So, yay, happy sunshine. So we are really, really happy with this one. But here comes the point now. We are now in 2026. So, and you probably joined the talk because you know that AI appeared. So with AI, a lot of things changed now. And we as platform engineers have to figure out now how we can get this rapidly growing and very fast-paced environment into our platform to provide also a nice golden path, a nice template for people to use this by still not violating all the things we established, things we found very useful. And here we come now in the talk topic. So what is AI platform engineering, and why you should care either as part of a platform team or maybe as a consumer to tell your people back in the workplace like, hey, how do you think about this one? Gwen already introduced me, so yeah, Engin Diri, you probably heard this from my broken English. I'm from Germany, and I work as a solutions architect at Pulumi, but that's just to myself. I have also some social credentials I forgot to put in, so you find me on Twitter, on LinkedIn, and all this stuff. Okay, so working on AI, working in AI, and you probably, I don't know how much your AI fatigue is currently now, but it's really, the speed of things changing, it's crazy. I mean, the last time we had this was in the golden time of Kubernetes, when every week a new project popped up and people tried things out. But now we are in the AI areas, you know, yeah, it's the Miller planet from Interstellar, I can't tell you. And then comes here this stuff, you know. So, hey, yeah, that's currently the cycle. So, yeah, Claude, Opus is really, really cool. You wake up the next day, literally wake up the next day, and then OpenAI released a new model. So the war of models, you're really like, wow, what's going on? So literally this week, they had Codex 5.4. At the beginning of the week, I'm with Opus, so it's getting a little bit out of hand, and you need to figure out now, and this makes it more important for the platform thinking because things change just too rapidly. And then this guy pops up, Peter from Austria, from one day to another. He really made a revolution because he built something, and we have a lot of discussion also at Pulumi because people try to figure out what is this. So my thing is always like OpenClaw. It's not about the implementation. The implementation may be flawed, maybe it's a thing. It's just that people have a need for always-on agents. That's a thing. So in the future, we will probably see some some companies, enterprise companies, bringing maybe also out a way to run agents, because that's what we wanted probably. We want to add an agent as a member in our Slack and be able to communicate, to talk with it, and it's always on, builds up a context window with the stuff we are talking, keeps memory and so on. 2 days ago, I think Claude Anthropic released the loop functionality, so you can now also put some cron jobs in that it's going to execute stuff. So yeah, OpenClaw is for me really some milestone in the already very quick world of AI. And then we have also these people. I mean, we're not talking now about the Indian Prime Minister, we're talking now about Sam and Darius. Yeah, the battle between all of them, you know, what to going to choose now. Is loyalty to an AI provider, to a frontier model, is this something we should strive on? Or should we just say, I don't care which model, we take the model which gives us the best outcome? and we are not bind anymore to loyalty like we did before, like, hey, I'm a die-hard Claude user. So that's a thing. I'm a little bit on my side. I switch also, so I have subscriptions for both. I have a max for Anthropic and a normal one for OpenAI, and I keep on switching in certain cases. But here we come again. This is another thing you need to know. So yeah, horrible, horrible situation. Okay, so with setting up, let me tell you how we tried to solve this with a customer. Okay, so a little story time so it puts better in the context. And yeah, better not run away. It's a story and maybe it's a little bit cringe, but it is as it is. I tried to prepare it as good as possible. So everything starts with this typical simple idea, you know. You have somebody who pings you and says, hey, we should extend, or you ping your manager and say, hey, we should extend our existing platform here for these new capabilities. We should have a way that people can use LLMs, can use AI for experimenting for as the platform team. Your boss, your manager is on board on this one, says, hey, that's great, let's go for it and do this. And then comes the big question, like, why we should do this now as a platform team to provide now a way to consume the LLMs. And I'm here back again from the German context. I can only say that data sovereignty is a big thing also in Germany. So providing here a way to consume LLMs on a safe way is very necessary and a very big topic. So one of the drivers for self-hosting in this case, why we want to extend, why the customer wanted to extend their platform engineering is to say, okay, we want that the data never leaves our infrastructure. So a lot of companies have this issue. Let's put the whole Germany thing or the whole European stuff apart. Still, there are some sectors in the industry who has this requirements. I talked the last couple of days also here with people who work, for example, in the medical area, and they also are now of this kind of problems. We don't want that that we leak accidentally some informations and things get saved somewhere or used to train. So that's also a big thing. I know, for example, my wife, she keeps on copy-pasting email to the LLM before they had approved way and which one to use, and that's not the thing you want to do. You don't want that people push confidential stuff and let the LLM summarize it or whatever they want to do. And then, of course, you have the regulatory compliance to do this, GDPR and so on, so it could be made by government and made because of the area you are. And, of course, we have air-gapped operations, so we need maybe to run mission-critical AI in completely offline environments. As I said, I worked in the company before which had manufacturing places. So we had, for example, meat factories, and they were completely an offline environment. So for this case, that was also very necessary to have something in place. But that was before AI. That was about Kubernetes, but you get the drift. So the strategic aspect of this, that most of the time, frontier models are very generalist, and some enterprises prefer to have a system which is only for their unique requirements. They need special. So we're talking here about this small SMLs, the small model languages. We want to fine-tune. We want to modify the weights using our proprietary data. We want to remove uncensored logic. So that could be possible that the system you are currently working, a frontier model, doesn't allow you to do a particular case because of the guardrails they implemented on this one. And then, of course, we want to train smaller, faster models to distill here from larger models. Okay, so that's some of the cases where the customer approached us here at Ballroom and says, okay, we need to find a way to make this possible. So here was the thing. So, okay, simple, we went really, really simple into this. Okay, let's create our first golden path because we already have a platform structure. So people can go to our IDP and just provision model and can deploy this on Kubernetes. Everything runs on Kubernetes. So we announce this as we are thinking about the product mindset announces in our internal Slack and tell, hey folks, we have now a golden path, you know, like you provisioned before buckets and all the stuff. We have now a golden path that you can provision your own model on Kubernetes. So everybody was really happy, but then reality hits again. So we got a lot of complaints here that people say, hey, what's going on? I ordered something, it cannot scheduled, I don't get a feedback, I don't get the URL to use, I cannot put this in, what's going on? And investigation showed that no GPUs were anymore available on the cluster because here comes the point, everybody provisioned, and that's a unit which is very scarce and run out very, very quickly. And in this case, the GPUs are gone. And also find out through our Grafana dashboarding that the utilization itself, it's very underutilized because people provision it, maybe they forgot about this, maybe they're not working on this, but still having the full machine running. So the traditional approach, they just don't scale. So we have Michael provisioned the GPT OSS 20B1, and then we have Jessica and everybody else, and everybody goes and through the golden path and provisions here a model to use, and then you can see the GPU utilization is poor, we have cost problems, no guardrails, and then what's the most important thing, because the resource hoarding, that's also a thing. We have in German a phrase we say, haben ist besser als brauchen. That means to have it is better than to need it. So you just get it and never give it back because the process is always a little bit sketchy. So you have the resource hoarding. The only persons who really like this is, of course, the GPU providers like NVIDIA. You know, they are like, yeah, man, that's the best thing you could do. So the first very naive approach of us in the Kubernetes world, here's a simple example of a deployment YAML where we put the resource tag in, and that doesn't work, you know. Having here one GPU for to use, it's not the way to go. Okay, so yeah, throw this. We need a solution. So sitting with the customer and brainstorming, the middle one, it's me. And that's the customers, they are much better than me, so I feel always a little bit out of touch here. But some ideas we came up with. So what if we increase the auto-scaling of the nodes and say, hey, wait a minute, so let's make auto-scaling. There are ways to do this, Carpenter or even the cluster auto-scaler. How about we set quotas to prevent GPU overuse? And here comes another point, how are we going to use MIG, the multi-instance GPU, to split things into time slices, for example. But then again, we find out that's also not the way, because what is the issue with auto-scaling? What is the new max? That's the problem. So if you have a lot of devs or devs using multiple, provisioning multiple stuff, you still hit a ceiling. There's only a certain amount of money people have. Again, with the quotas, you still have a lot of, so even with one GPU per employee, this is very problematically. And then comes the idea to say, okay, let's use, people can order slices, but if you go too low with your slices, it could be that the models are not reacting anymore that good. You get some latency and all the stuff, or what happens when people still order multiple slices, and that's also something tossed in the bin for the ideas. Ideas we kept, so to say, okay, what's an idea we should do and continue? What we first said, okay, we need to collect all the GPUs back. That's not going to work. We cannot let people have one GPU per person on this area, so let's get them all back. And then another point is, okay, how about we deploy each model only once and have some kind of API gateway for AIs in front of it, so let people consume. You see, the things maybe are like, wow, that sounds quite obvious, but in this case, it was not that obvious because this is the experience folks had to need. And here comes the platform. We need now a way that people can have access to these models also. So, and yeah, that's, you will see like, hey, wait a minute, AI platform engineering sounds a lot like normal platform engineering. So, and that's the thing. Similar to the whole IS stuff, sorry for the S in lowercase, we now have a new service in place. Let's call this Model as a Service, MaaS, and take what we learned from infrastructure provisioning, infrastructure exposing as a service, now also for the AI world. So yay, the new way, Model as a Service. Okay, so we now have pre-trained or AI models, having them accessible via APIs, and then eliminating here the need for every team to have their own stuff running, and then also blocking our GPUs. And yeah, that's one phase. It doesn't sound new, so like, oh yeah, that makes sense. Again, as I said, trying to get this in. And here, let me see what was on this one. Yeah, so when people reach out now to say, hey, we want a new model, you can say, hey, have a look in our system. There's already a model, and then you get also access. You will see the implementation, because this is the most interesting part. And then before it was, I need my own model, and now I need API access. This is really the brain shift that people can come. They can reach out if there's a new cool model and talk with the infrastructure, with the platform engineering team, and then decide to say, okay, let's put this in, and I can then announce as part of my release cycle as a platform team, hey, there's a new model coming out. So yeah, we are now completely wiping. That's cool, that's what we want. But here comes now the next point, which comes the last couple of months to us on this solution. Now people ask still for access for frontier models. Because here is also the reality, you know, you can provide stuff and then they say, yeah, but we have cases where we want to access because we have a specific agent running, so we need access to Opus. There should be a way to do this. That's, again, reality. You can whatever provide, requirements are changing. And now comes the whole background agent stuff. People are like, hey, we need now a way that we can also order background agents and let them run. I want to order 10, I want to order 15, I want to give them a specific case, and they should run. Is there a way in your platform to allow this? And another point is like, hey, can we have a central way to manage our Jupyter notebooks that our, for example, the ML team can order them as similar as the other stories we have here? So yeah, we are back again to shit. Now we need to think about a solution. But we come up with a very cool solution on this one, and I want to show you now one reference architecture, what we created here. It's just an example. Okay, so as you can see, we have in the middle, we have our Kubernetes cluster. Everything runs on AWS in this case. So you see here, we have different node pools, and let me come here a little bit better. We have different node pools for the use cases we want to create. So we have a system node pool where the applications run, which are necessary. We have a general pool where our AI IDP is relying on. And then we have also here the agent sandbox. You will see this in more detail, what I mean with the agent sandbox, which is a special pool using gvisor to provide a very isolated and very secure area for sandboxes, for agent sandboxes to run. So that's a new addition to this one. And then we have also the GPU pool, which will be used from our local inference serving using Kserve. And everything AWS EKS using Carpenter to on-demand spin up the right pools, the right nodes when there is workload, and also scale down when there's no workload. So think about people running their notebooks on GPU because they want to train, they want to do some specific work, they're going to boot up, and now you can say when there's no, because you have your Grafana connected, you have your monitoring connected, you can now say, hey, when there's no workload or when people are back at home, we can automatically scale this down, and Carpenter takes care to remove the node pools, and you're not paying for, because again, GPUs are expensive, and that's the thing. Okay, so one of the building blocks we used here is Kserve. So Kserve is a whole platform which enables us that we can run generative or predictive workload on top of it. We are focusing here more on the generative part here, but you can see Kubernetes is again our base layer. We have now auto-scaling possibilities. We use approved tools, either the inbuilt stuff from Kubernetes, or we can go with Knative. We can use KEDA for auto-scaling depending on the load and all the stuff. We have networking. We have an inbuilt Envoy gateway, which is really, really nice. And then we also rely here on LMD. I'll talk a little bit more later, and VLLM. Okay, so yeah, with Kserve, we have now here our unified interface for deploying the models, and as I mentioned, again, supporting all the goodies we have from our Kubernetes world. Most importantly, what I like a lot is the scale to zero possibility. Okay, and another benefit from Kserve is it's part of the CNCF Foundation, so you can be sure they don't do a rug pull here and maybe force you later to pay on. It's part of the project, and you can use this. That's very cool, and contribute to it when you see the need as a company, because your business rely on this one. Another part which Kserve has underneath is LLMD, which is here our for distributed LLM interface at scale. It's powerful. I'm not so deep into the nits and grits of LLMD. I'm just using it, so I'm on the practitioner side. But it's one of the, how do you say this, in his area, the most performant tool to use. So Kserve really used also different building blocks on their own. And then VLLM, that's the one which a lot of people using now. You can run it on their own. Kserve has it here also as a serving framework and has a high throughput for your for GPUs and all the stuff. So there's a lot to tweak. I was last time in a call where people literally had a whole talk about tweaking VLLM for the best results. So a very cool product here. Another advantage of Kserve is that we can now say we can run workload either on a single node, we can run them on a multi-load workload and disaggregate workload. So there's a lot of things possible if you want to run large models on your machine. So it gives you all the necessary steps to work, because it implements underneath. You can activate the leader worker set, which is a sub-project from the CNCF, which then allows you to split your LLM workload. Also very cool. But we have also an issue here. So there's always shadow where light is. In this case, one of the biggest issues we had was the cold start problem. So one thing is we pulled the stuff from Hugging Face during startup, and depending on the model size, a large model was really slow cold starts, which affected people. They had to wait a lot to work on this. Network latency when we start to download the stuff from, for example, Hugging Face, and then, of course, poor user experience when you auto-scale, for example. So that hit us very hard. And here comes a new functionality we used that was recently released in Kserve, that we now can package the model weights as an OCI container image. That's very, very cool. So we can then mount the data directly in the container. We don't need to do any external network calls to Hugging Face or to an S3 at startup. And we can leverage our existing infrastructure with the container registries to distribute this inside our company. You can upload this to Artifactory. You can upload this to your ECR, so depending on your setup, that's very cool. And the infrastructure is already here. And having now the model weight completely as an OCI image was a big game changer. So, okay, I already made the stuff, so that's the how do you say this, the benefits. One cool functionality with Kserve is it's a drop-in replacement. You just need to change one flag, and it's going to take, instead of saying HF column // you say OCI // and you point to your OCI registry, and it's going to pull this via an init container. That's a very cool functionality. While testing it, there was another issue. We find out that OCI image was nice, but still the download time was still something not acceptable here for the customer. So the next step we did was to bake the images for the nodes completely in beforehand. So what we do here in this case, we spin up, it's a project, AWS provide here. We spin up an instance, we download all the models we want to have available, and then we we shut the instance down, we save the image as a snapshot in the snapshot registry of AWS, and then let Carpenter know if you're going to start now an instance of type GPU, for example, GPU pool, don't use the default operating system on top of it. Use the AMI we configured, but with this snapshot, because this contains now all the models. And when you start the container, there's already present, and it goes even quicker. So we reduced the cold start time on this one very, very drastically. There are some other things now people also consider to have I removed the slide, it's called Runner AI, but we didn't have a good implementation. It was still too early to use this one. So let me turn on the light one to see this better. And yeah, that's the setup for pre-baking. Another idea we had was, was split inference, to say, okay, let's do GPU, CPU offloading, so then we can run the models by replacing their weights in the RAM, flexible memory speed trade-off, but also find out by testing out we have higher latency, slower tokens when data moves between the VRAM and the RAM, and more tuning and ops complexity. So that's the thing why we left also the GPU, CPU offloading away. Okay, another very important building block, and this project really blows my mind, because you will see now how the project helps to expose frontier models to the customer. So Light LLM is an API gateway, and it's also an open source API gateway. And here you can see all the possibilities we will also use in our IDP. So you can define model endpoints, you can define agents for people to use, you can set up teams, you can have the way people can get access to them on the self-service. But as you can see, the UI is quite complex. So it's again a thing where we say we should not let people run on this UI. And for this one, we will see the AI IDP we created. But here, one of the benefits of Light LLM as an API gateway was here we have the key management for the API tokens per team, per developer. We can route now, we have load balancing across models, so if one model goes down, we can still expose another one. That's really, really cool. Metrics, very important. As I mentioned before, we are not an NGO. We may have to charge back the usage, so having here a possibility to track everything gives a lot of possibilities for us as a platform team. Guardrails, very important, so we can do content filtering on this side, so we have a more structured way of letting people use the systems. We can set up rate limits. Chargeback, very important. We can see what people are using. We can then send the costs back again. This is a more important, as you see, GPU nodes cost a lot, and frontier models, think about Opus with 1 million context window. That's quite expensive, so having this set up is very useful. And here comes also another point, the OpenAI compatible API is also very cool, because you can use this now as a drop-in replacement, maybe for your project. You spawn as a shadow AI, you know, you already did some work, now people come and say, hey, we have to collect everything, all this rogue usage of OpenAI, we want to collect this. You can take the API endpoint you get from Light LLM and just drop it in, and it's still going to work. That's cool. And now think about you run, for example, Claude on your machine. You can change the URL. Chargeback, as I mentioned before, you can set up now your own prices. You can say, okay, this amount of tokens costs you a certain money because it's your time, maybe the model, maybe the GPUs, if you're self-running this, because it's also important. Now I provision for GPT-20B or whatever, or Minimax model. I'm now provisioning GPUs. they cost money, and I can tell now this is the price, and people see in the list what they're going to expect, what is expensive. You can also say, I expose always the self-running ones because they are cheaper than using, for example, the frontier models, and you get all the information. Okay, so now you saw all the building blocks. So let's see the last building block here, our AI IDP itself. So that's the architecture of our AI IDP. We have the user comes with a CloudFront HTTPS here in your custom domain, your internal domain. We have a front-end application here written with React where people can work. Again, this is something you can adjust for your needs. We have a backend, again, an Express.js backend. The platform services we are exposing now is Light LLM Gateway, Jupyter Hub, Agent Sandbox. We have a database in the back to track everything to make it consistent. We have our model serving I just talked, K-Serve, VLM runtime. And here comes one of the things I'm spoiling already. We also have access to AWS Bedrock. So that's the thing, how we're going to expose some models, some frontier models to the customers. So here, AWS Bedrock is the key, the OCI model cars you already saw, Carpenter, and underneath we have the pure infrastructure layer here with Amazon EKS, all the VPC and so on and so on. So that's our whole platform in its building blocks. Okay, so coming back again to the question I had at the beginning, people come and ask now, I want access to frontier models, I want access to background agents, I could do this, but I want it as a service, and I want a way to have Jupyter notebooks provided. So here comes the point with, where are we? Yeah, with the access of AWS Bedrock. Again, this example is in Amazon AWS, so some things are easier, but it should be applicable also for the other cloud providers because Vertex AI, Courtney Vertex, and then Azure Foundry should have a similar way. We use pod identity, so our Light LLM has a pod identity set up in the container to communicate with Bedrock, so there are some IAM roles set up that we can easily communicate with the Bedrock agents we want to expose and can register them now in Light LLM as a model and consume it through Bedrock. So what is the advantage of people using, for example, the Bedrock case? Everything is in a cloud budget. They don't need to go to specific procurement. Yes, of course, you could use Light LLM to provision directly from OpenAI or from Anthropic, but here in this case, customer prefers because the whole cloud spend is our own budget and he can run this through this. No need to approve because most of the companies, especially enterprises, they have a carte blanche for using the cloud services because it's already everything settled down. No need to run, so you can get quicker access to the stuff. Jupyter Hub, that's very interesting. So here we use a project called Jupyter Hub for Kubernetes, which provides people a way to spin up containers which has Jupyter notebooks running into it. You can then choose at the beginning what kind of machine you need. Maybe you want to run on a GPU and all the stuff. And because of our Light LLM integration, we now using inside our Jupyter notebooks, we're using models which are exposed via Light LLM. So again, a very cool point. Everything is tracked again, and people can self-serve them, their notebooks for their needs. Agent Sandbox, it's a Kubernetes project from the CNCF, so it's also part of the foundation. And with the Agent Sandbox, as I mentioned before, the mass backend acts now here as a controller for Kubernetes. When it gets a request for creating open code or open claw instance, it's going to create the CR on the Kubernetes cluster and run here different steps. And most importantly, everything is run on gvisor because that's one of the things we take care that we have a very secure environment, a very secure sandbox. So we're not relying only on containers and say, hey, let's do with some policies to avoid that you can break out of your sandbox, because that's the biggest fear, breaking out of your sandbox environment. With gvisor, it's very, very secure. the best thing could be you use something like Firecracker, you know, having definitive micro VMs, but in this case it was a very acceptable compromise to go here because we didn't need to provision a dedicated one. Just as a note, if you want to try this on your own infrastructure, not every cloud provider has the possibility. So the major ones, of course, have the way that you can run your gvisor, extend your nodes with gvisor, but you have to check which cloud provider you're using. AWS is very cool on this perspective. And I think on Google you can even run Firecracker stuff. And then you can see the two types of agents we are exposing currently is open code via UI, open code via CLI, and OpenClaw because people want to try, and we don't want that people run OpenClaw on their machine or provision some EC2 instances and just run the stuff on there. Everything again is Carpenter managed, and everything runs on this gvisor stuff. How does it look like in the UI? So that's a simplified one with stripped down. We have our models. We see what is available. I will show this in the demo. You see much more details. You have the agent view where you can spin off now new agent, again, completely self-served and decide what I want to do. We have the notebook tab. And here comes another point. We have finally the observability in for the people to understand their spend. So we have this FinOp tabs where people can see which API key used what kind of tokens, and what kind of prices I'm expecting. You can highly automate this in a way to send monthly mails or whatever, automatically connect to your internal system where you charge people for the usage of your service. You can define teams. This is everything done again on the side of Light LLM. So in the AI IDP, there is no need to configure this. This is something we as platform engineers can do, and you can see in which teams you see, here comes the important part, budget. You can set up budget. You can say, okay, the marketing team has a budget for $200 for using, and if the budget is gone, it's gone, and you have the different teams. You see in which subscriptions you are, and here, most importantly, you can now create on your own keys and assign yourself to the team and see usage per key and then select. So in this case, the marketing productive key has only access to Cloud Sonnet because it's not necessary to have this high performance model lying around. Here in this case, Sonnet is also good, but they need access to Amazon Nova Canvas because they want to use some graphics. Okay. So let me show you this in action, because talking is cheap. And let's mirror. Okay, so we are here. First of all, this is the view from Light LLM. I showed you before. You see here all the models connected. You see how much pricing you put in. This is everything you can do. So you can use whatever metrics you are, the GPU price of the VM or the price Claude or the Bedrock price, what AWS is charging, and then set up the stuff. That's one part. You can set up MCP servers for people to use and say, okay, this is the way, and then they can use Light LLM with the HTTP protocol to use for your for the MCPs if they want to run this, for example, in whatever system they have, guardrails and so on. We see the teams. So here you can set up the teams. You can give them a specific budget. And another interesting point is the AI hub. Here we expose every model which can be publicly consumed. So you can have a lot of models inside your model endpoint here, but people cannot provision this because it's not exposed as a public usable one. So that's a way you can control this. You can control the access and so on. So quite powerful here in this way. How does it look like in the model now? As I mentioned, you see now, this is the tile for all the exposed models. I can click now as a customer and see here the parameters which are supported. I see a little snippet to use, so it's very friendly for people to start to use. That's one thing. I can see here in the Nova, I see the price. Here you see Bedrock is charging costs. Do you see this? Yeah, costs per image. and then you can guess the pricing. Okay, we come now to the agent tab. So we see I started already a TypeScript open code instance. So if I click on open, let's hope everything works. Yeah, it's here. And I can say, hi from Pasadena. And here the inbuilt LLMs are reacting. You can also configure this one to say, hey, use the one from Light LLM, but that's one thing. I can also create a new open code agent and call this, let's call this test2, very creative, and say, I only need the terminal. Here, another functionality which was very important is skill support. So I have now the option inside my platform as a platform engineering team to define skills and let people use the skills. So if the customer says, hey, I would like to use, I want to have a background agent running and it should be mainly in the TypeScript area, let's take this one, and if I run K9S, that you can see what happens in the background. And let's go into the, here you see it's automatically scheduled, and hopefully if the demo goes, yeah, you can see now it's going to install the skills on demand during the init container part. You could also go a different way to say, I want the skills somehow differently persisted, but here in this case, accessing npx command to install the skills. And after a couple of seconds, this one is running also. And while this is running, let's provision also an OpenCloud agent and say test3. Now we need the token for the gateway because that's the way OpenCloud is working. So we can copy now. I saved my token. And this one should also, OpenCode started. So let's have a look at OpenCode, the CLI version. So if I want to access this now as a customer, you see now I have the CLI working from OpenCode and can say hello, and it should also do the work. You saw there was a field where you could put your Git repository in, and it will automatically during startup also Git clone it so you're ready to work and then spin up here. But as you can see, this is also working nicely. And last but not least, let me see how test3 is going. Yeah, this one is also ready. And now I can open OpenClaw, put in here my connect token I get in the beginning. We see it's up and running. Let's go to the config, and I prepared here because we want to use, as you see, I want to use Light LLM as an AI model and not connecting it here to nothing because there is nothing. So let me put this in, save. Where is, oh, so that's the key from Light LLM. Okay, so this is also set up, and I can go in the chat. I say, hey, from Pasadena, who are you? So now we come into the setup, hopefully, of, yeah, so welcome from Pasadena. And then he was like, I'm freshly hatched. Please give me a soul ID and all this stuff, 10 minutes. Okay, so here we have now a way, run in a sandbox, always on controlled access for your teams to use. So now people can use OpenClaw and configure the stuff, what they need with connecting the settings, or you can predefine them for people to use. But yeah, that's a way how to enable modern stuff with your setup. Okay, so I'm not changing here. That was the demo. Okay, to wrap up, so what is the real world impact? Again, I always mentioned we don't do this because, we do this because we like to geek around as engineers, but we also want to achieve something for management, for people who are paying our salaries. Here's like faster time to production in any cases now, be it by creating customized agents, by using our self-hosted model, which have a definitive purpose. Oh, I forgot to show you something. Sorry, so let's head to the notebook. So that's something to show. I spinned up a notebook already, and here I have already also created a demo notebook. So in this case, installing OpenAPI. As you can see, I use the Access for Light LLM again. So setting up this, and now we can say a futuristic city skyline in Pasadena. Let's see what happens. Pasadena. Okay, and now because I have access here now to the model for image generation, it should hopefully give. Yeah. So now we have. Yeah, that checks out. That looks like Pasadena or Alto Pasadena, or I don't know. Okay, so the Jupyter notebooks are also working, and as you can see, they're running here. Part of here is the Jupyter notebook for marketing, because marketing wants to create image. Okay, so faster time to production in all areas. If developers can start, developers consume now the latest trends in the AI world, controlled, exposed by you. They are not disconnected. They don't need to do shadow AI. We reduce the cost because of better GPU utilization, having here an eye on the usage, setting budgets, better governance. That's always important. You can push every story in your company if you attach it to governance, compliance, and security. So that's a hack I learned in all the years. And yeah, improved security. And now coming back to the statement, so AI platform engineering empowers internal developer platforms to enhance the developer experience and productivity and drive automation and standardization with AI. That's very important. And then we're still not breaking with our platform engineering principles here by including this new, because at the end of the day, for us as engineers, AI is an additional type of workload we have now to manage. You saw OpenClaw and OpenCode and whatever system. For us, on the goggle we have on, it's workload, and we see we still enable people self-service, so everybody around the sun can do, don't need to ask me. Automated infrastructure management, everything is set up and follow the guardrails, standardization, and then of course, I need to 10,000 times to put it on. We have, again, the governance and observability free. And here comes another point why I always mention this, because your platform is already maybe approved from your internal security team. So all the stuff, so any team who are now working on this doesn't need to go again and say, hey, my project creates an AI agent, I need approval, I need a penetration test or whatever, because most of the time, when you have a platform engineering team and a platform in place, this one is already approved. They do the heavy work with talking with the pen test people and so on, and you as a team can consume it and be sure that it follows the standards, because they went through. Key takeaway, shared infrastructure is unequal shared resources, platform engineering enables scaling AI, and yeah, self-service and visibility for accountability. And with this said, I'm open for questions or not. Please don't. No, 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 Gwyn, no.
Any questions? I will come to you with the microphone, and please use the microphone to speak so we can capture you on the recording.
Great talk, thank you.
Thanks.
Do you have example deployment code for the demo anywhere? Is that on GitHub somewhere? Or
Yes, it's on GitHub. Let me. Yeah, here. So if you go on my repository DVEN and look for what is AI platform engineering, that's there you can see the demo reference, and it's written in Pulumi. So that's one thing, but you can, if you configure everything, you can then Pulumi up it. And you have different layers. You have the infrastructure layer, the mask layer, and the building of the baking of the image using code build, and then pushing the stuff. So everything is there.
Great, thank you.
Or you ask Claude to summarize it for you to use it in another language of your choice. When there's no questions, I
Any
love
other
your
questions?
audience. That's good. No questions. Oh, no. Don't
Oh, yeah.
take my streak.
So what were your cost savings of building your own service instead of using something like Amazon, Bedrock, since you're already on AWS, to control access to the models? It's like,
Sorry, I didn't catch
so
the-
since you wanted to control access to the model for, to reduce spend,
Yeah.
how much cost savings was it compared to like just using Amazon Bedrock and hosting your model on that and just using that to scale your API?
The voice here is not very good. I didn't get the question.
I think the question was, how do the cost savings compare using this setup compared to just using Amazon Bedrock, which has a lot of these
You
capabilities?
can fix, because you're running completely on AWS, you can just push it through and say, I'm not charging additionally on top of it. Say, okay, we are not going to make a profit from our internal customer, but what we have now is a unified way to get access. So the person doesn't need to go to another way to get access with their account they are using, having the roles to consume Bedrock. So that's the only thing. So it's not all about making profit and so on. That's just one thing. But you could say, okay, the price from Bedrock, I will just push it one by one through, but people see at least the spend, and I can regulate this still, because it maybe doesn't come to a place where your AI agent goes crazy and burns tokens, because now you have a guardrail, and it's which you may not have before. That's a thing. So it's all about providing a story. Sorry if the cost aspect was a little bit too prominent, but yeah.
Any other questions? Yeah.
So you're running Amazon instances with GPU capability, right? And you're running your own models on that,
Yeah.
and providing it. So did you look at like seconds to like first token or whatever, and like tokens per second, and compare that to what you get for the same cost with one of the other providers or with Bedrock? And,
Yeah,
like,
that's something. Yeah, that's what the customer has to continue on the story to say, okay, how does it compare? Is it good enough? So in this case, it was first. Again, things evolve very quick. So in this case, it was all about, we don't want to use the frontier models. We want to provide a way for people to use this. So that's how the whole project actually started. So that's why it's at the beginning. It's very focused on running the stuff on your own. But yes, of course, you have to check if the metrics are fitting your needs, and then rediscuss this internally to say, hey, this is something it's not acceptable, or we need to step up, beef up the instances to have a better feedback. Yeah, that's.
Well, I mean, in the demo, it seemed pretty quick, so that was pretty impressive.
That's yeah.
We have time for one more, if there is such a desire.
Then I can run now away. That's
All right.
okay. Then
Please, everybody, join me in giving Engin another hand.
Thank
you
you.
so much.
thank you.
Check, check, check. Check, 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 check.
And let it go green, and then you can talk now.
Okay.
And you
Yeah.
can hear a little slight echo.
Perfect. All right. Yeah.
Mike's good?
Yep.
Okay.
Sounds good.
All right, welcome back to the Cloud Native track here in Ballroom B. Up next, we have Sharif Shaker giving us a talk on plug and play Postgres with CNPG-I. I will say, please hold your questions till the end. And on that note, are you ready?
Yeah.
Take it away.
Let's go.
Let's give him a round of applause.
All right, everybody. Thanks for coming out, and hope the conference has been going well. Today we're going to be talking about the Cloud Native Postgres interface, an interface that allows you to build custom pluggable software into your Kubernetes-based Postgres databases, allowing you to hook directly into the lifecycle and integrate your own custom code and functionality directly into the database. So we're going to be starting out here, going in some foundational work, talking about running your data solutions in Kubernetes and why you want to be doing that. We'll then introduce Cloud Native PG, the open source software that allows you to run Postgres in your Kubernetes environment. We'll talk about its declarative design, as well as the something that's built into the system, this idea of an operator versus an instance manager for managing your databases, that will tie into the work that you'll be doing as we talk about plugging in custom logic into the database lifecycle. We'll then introduce CNPG-I. This is the Cloud Native PG interface. We'll talk a little bit about why it was built, as well as go into the gRPC protocol that's used for the Cloud Native PG core system to talk to your plugins. We will walk through the deployment of the plugin, as well as get into a little bit about the architecture of how the plugins interact with the operator. We'll do an example of the Barman Cloud plugin, where Barman Cloud is a backup system that allows you to back up your Postgres databases to the cloud. So we'll talk about what the plugin for that will look like. And then we'll do a quick demo showing a very simple plugin example and how you would deploy it and run it in the Kubernetes. I have here a QR code for some slides if you want to get a link to them and see them up close. There are a couple diagrams in here that might show up a little bit small, so it could be helpful. All right, so let's move through it. So there was a time, like early Kubernetes, when was designed for, generally speaking, stateless applications. So running actual stateful data workloads was frowned upon at one point, but things have changed a lot. And now running databases in Kubernetes is common practice. There's a lot of advantages that come with running your database in Kubernetes. The big one being keeping your data solution and your applications running in the same place on the same system. So you can have your kind of declarative management of your databases, which is a major feature, managing things like storage, CPU, memory directly within Kubernetes. And then you have your single pane of glass for managing your metrics and your logging, networking, as well as the portability component. So all that to say is that the question has become less one of whether or not you should run your database in Kubernetes, as it is one of how to run your database in Kubernetes. Because ultimately, the goal of running a data workload in Kubernetes is making sure that you don't risk any potential for data loss in the case of pods going down or disaster striking. So this is where the Cloud Native PG project comes in. The Cloud Native PG is a fully open source Postgres project that is designed to natively run Postgres databases within Kubernetes. It was recently included as a CNCF sandbox project, and it gives you that declarative control of your Postgres databases within a Kubernetes environment. So it uses these custom resource definitions for clusters, where you define the cluster definition that you want. In this example here, you specify the number of instances you want as well as the storage size. You can also configure a ton of different things through this cluster manifest, such as your CPU, your RAM, any number of Postgres configurations that will define how your database will be configured. And then you have the cloud native PG operator, which is a Kubernetes operator that's running and reconciling these cluster resources, making sure that Kubernetes is running those Postgres databases as pods within your environment. So specifying 3 instances is telling the operator to run 3 different Postgres pods that contain your database, where 1 will be a primary and then 2 will be replicas, and it will ensure automatic failover and consistency across those databases. So you essentially have a fully fledged Postgres database natively in Kubernetes, and you can kind of not worry about the rest, not worry about the data loss issues or what's going to happen if a pod goes down. Everything is going to be managed by the cloud native PG operator. There are also additional resources associated with the project, including things like backups, and in this example, a scheduled backup, which would allow you to schedule a time to consistently take backups of your database. So that is the open source project. And just to give you kind of an idea of an important model within that project when it comes to running your databases, this is going to tie into how you would develop a plugin and how you would actually leverage different functionality within that plugin. So there's this concept of the operator versus the instance manager within Cloud Native PG. They both exist as a single binary within the project, but they run at different levels. So the CNPG operator is kind of in your control plane. It is reconciling those cluster resources as you would normally expect in a Kubernetes environment. And based off of that, it is making sure to provision your Postgres pods. It specifies the container for Postgres and sets up your Postgres image to run. But there is this other component to it called the instance manager, which is actually running within that Postgres pod and is actually the process that spawns Postgres. So the instance manager can be kind of like the intermediary between more of your like Kubernetes environment and the Postgres instance itself. So it's going to be responsible for things like your liveness and readiness probes. It's going to be doing managing like your backups or your wall archiving that is done by the Postgres instance. But that is going to be managed by your instance manager, which is also spawning Postgres. So this is the basic model, and it's important to just kind of keep that idea in mind as we move forward, this idea of your operator happening in the control plane versus your instance manager actually running on the node in a container with Postgres. So that's a great start. You have your Postgres database running in Kubernetes, but there's a lot of situations where just a plain Postgres is not going to be enough. You're going to have a lot of different requirements for different projects or different organizations, whether you're talking about custom backup requirements, auto-tuning requirements, or desire for features around making sure that your database configuration maybe automatically scales or changes based on the resources in your environment or the performance of your environment, security requirements to do with certificate management, or any number of like logging or auditing requirements that you have within your system. So in the past, the solution to this kind of these kind of issues might be if you need a very tight integration with your database, you might have to fork the project. So you would fork the open source project and you would integrate whatever custom logic or functionality that you need, and then you could run your fork as your own, basically your own separate thing. But that comes with its own challenges. So if you're going to fork the project, you're going to have to maintain that fork. You're going to have to keep up to date with the upstream, and it can generally become a bit of a hassle. So this is where the Cloud Native PG interface comes in. It's a gRPC-based protocol that basically defines an interface between the Cloud Native PG operator and external plugins, which you yourself can build and deploy. So you basically have this project here that we linked below Cloud Native PG/CNPG-I contains these interfaces, and you can go in and build your own software that implements those interfaces, and then the CNPG project will be able to hook into whatever logic that you provide, and throughout the lifecycle of your cluster, integrate your own custom code. So if we look a little bit about the background, we kind of touched on this, but the original reason for the CNPG-I project to come and be attached to Cloud Native PG was to do with backup and recovery. So when it was originally built, the need to have a cloud backup system built into Cloud Native PG was very important. If you're talking about running your database in the cloud, being able to take backups is extremely important, but it's generally speaking, apart from like a simple PG dump, an actual backup system isn't really incorporated in the core Postgres. So the decision was in the original inception of CNPG, the design was actually to include Barman Cloud, which is a backup solution for sending clouds to object storage. The original solution had Barman Cloud built directly into the CNPG project, but this cut out a lot of flexibility and kind of muddied the waters when it comes to what CNPG is. So to keep kind of the core CNPG clean, the idea of introducing a plugin that you could basically put in whatever system that you wanted for managing something like backups could be integrated. So you would have your Barman Cloud plugin that would integrate into CNPG and allow you to take backups using Barman without actually necessarily being incorporated into the core CNPG code base. So ultimately, this idea of being able to integrate these custom things for backups, for example, was expanded and turned into this very general purpose interface where you can manage things like backups or walls or metrics or Postgres configuration, and it really extends to any number of different areas. And the ultimate goal being these kind of pillars of reducing the complexity and of the core CNPG project, allowing the ecosystem to be able to expand so that different integrations and tooling could be incorporated into CNPG without necessarily requiring you to fork anything or manage anything independently. And it just essentially makes this kind of pluggable and very flexible system possible. So as far as the gRPC component, because this is a gRPC based system, I just kind of walking through the basics of what that would look like. So gRPC is an open source, originally started by Google. The RPC portion is remote procedure call, which is essentially allows you to define, RPC would be making a function call remotely. So you would define using what's called protocol buffers, basically the structure of those functions and those services that those functions are a part of. And that would give you kind of like the API for defining what your application is going to be doing. So the way that the CNPG-I project works is it defines a lot of these gRPC services with these functions that you, building out your plugin, would implement. So you would implement one of these function calls that could then be called by the Cloud Native PG operator. And the cool thing with protocol buffers is that you'll define what is kind of described above in this service. This is an example of actually one of the services within CNPG-I. So you would define the service and the inputs and the outputs, and the compiling of those protocol buffers actually can produce code in whatever language you're using. So the common one here is, this is an example of compiling the protocol definitions into Golang, so you can build out your plugin in Golang in order to implement whatever this functionality is, and the operator will then be able to call that remote functionality. So now, if we look at kind of into look at the interfaces that are available to build into your plugins, Now, something important to note here is this going back to the operator versus the instance manager levels. These interfaces that are defined with the gRPC will be called by either the operator or the instance manager. So each service has its own set of functions defined within it, and some of these functions are going to be called by the operator. That would be things like this operator interface, the operator lifecycle, or the reconciler. These are all containing functions that get called at various lifecycle points within the operator's management. If we look at stuff like restores or backups or wall management, this is all functionality associated with interfaces that would be executed by the instance manager. So the cool thing with CNPG-I is that you don't actually need to implement all of these. You only have to implement the ones you care about. The one exception being the identity interface, which needs to exist for any plugin, whether it's implementing instance or operator level functionality. The identity interface is what allows for CNPG, the operator, to actually discover your plugin and identifies specifically what your plugin does. So it will include within that identity interface the specific capabilities of your plugin and what the operator needs to do in order to actually implement and call your plugin services. So if we're going to look at a little bit about how you would actually plug in practice, generally speaking, you'd build your plugin as a deployment within Kubernetes. It would define a gRPC server that exposed those functions that were implemented based on the definitions within CNPG-I. And then you would deploy it as, the recommended approach here, that is what we're going to focus on, is you would deploy it as an independent deployment within your Kubernetes cluster. So you'd have a deployment of your plugin that was running alongside the operator, and it would have a service with a cnpgi.io/plugin name label that is required for the operator to discover your plugin. So your plugin, the CNPG operator is looking for these services, and if it identifies a service for a plugin, it knows this is where it needs to go to register that plugin and hook into that functionality. So once your CNPG operator has discovered your custom plugin, in order for that plugin to be utilized for a particular cluster, it has to be configured as within the specification of that cluster object. So in this case, we're adding the CNPG-I plugin.io as a plugin for this cluster. So when the operator is running, it's going to see that this plugin is defined for this cluster. It'll be able to look at the registered plugins that it has and make sure that it is going to, any time that this particular plugin has functionality associated with a particular part of the cluster lifecycle, it will go ahead and execute the acquired functionality. So just for a quick diagram here, we can see it's very similar to what we looked at before, but now we have this CNPG-I plugin that is discoverable through a service. So the CNPG operator discovers the plugin by having the service with that particular label, which tells exactly what the plugin is, that can send requests for initially getting the identity of the plugin and then executing functionality based on the reconciliation. But something to note here, notice that this is just at the operator level. The instance manager doesn't have access to the kube APIs and the access to the service to discover. So actually implementing plugins for instance manager level functionality requires a little bit more work. The general procedure for doing that is to actually have your operator level plugin inject your instance level plugin into the Postgres pod. So the instance manager can discover plugins by finding local containers that actually implement the plugin logic, those plugin interfaces. The way that it works is that you actually use a Unix domain socket. So this is done by having a shared volume mount on both your Postgres container as well as your plugin container. And the instance manager actually knows to look for this /plugins volume and discover plugins through it. So you would add your new plugin as a injected container that has a volume mount at /plugins, and then instance manager is able to discover that plugin and send those requests to the plugin directly using things like doing things like wall management or backup handling. So you can see there's like this two-phase approach where you're first injecting your plugin as a container using the operator level plugin, and then now the instance manager can connect to it. So if we look at what this looks like is a diagram, this is a similar situation to what we had before, but now my operator level plugin is actually going to inject the specification of my new plugin container into the pod as part of the lifecycle management, and it hooks into the creation of that pod. And now my pod is configured with not only the Postgres container, but also my plugin container. And using that volume mount that we described, the instance manager is able to now send requests to the instance level plugin to do things like backup and wall management. So this is the general flow. This is kind of like the fully fledged plugin setup that you would have. Now to walk through a concrete example of an actual plugin, this is kind of like the original plugin would be the Barman Cloud CNPG-I plugin. So Barman Cloud is, like mentioned before, a backup solution for Postgres, and it was originally built directly into the CNPG system, but has since been moved out into a plugin. So the way that the Barman Cloud plugin works is it basically will take backups of your Postgres and send it out to object storage like S3 or GCS. In terms of some of the interfaces that Barman Cloud implements, you have the identity interface, which is required for all the plugins. But then it has a bunch of other interfaces as well. So the operator lifecycle is going to allow the Barman Cloud plugin to hook into the creation of resources on the cluster. In the case of the Barman Cloud plugin, this would be the pod creation, so that it can actually inject that instance level plugin directly into the Postgres pod. It also leverages this reconciler interface, which allows you to hook into the reconciliation of clusters or backups associated with a cluster resource. So in this case, it can essentially extend the reconciliation process of a cluster, and it includes something, a custom resource specific to the Barman plugin, which is this object store resource, which refers to wherever object storage you're going to send backups to. Now at the instance level, the Barman Cloud plugin is hooking into functionality around backups, restore, and wall management to be able to send information to object storage and also retrieve information from object storage when recovering a cluster. So we're just going to take that new idea and extend our diagram here. You can see the Barman Cloud plugin is doing just what we looked at before. It is injecting a container containing that instance level plugin into the pod. But it's also reading the object store information from this custom resource. It is now configuring the instance level plugin to set up a new Barman Cloud container alongside the Postgres container that is able to be discovered by the instance manager, and requests for things like taking backups and archiving walls, which go through the instance manager, now can be sent to Barman Cloud, and Barman Cloud plugin is able to archive those walls or send those backups to object storage. So that is the full kind of setup of the Barman Cloud plugin. Just to give you kind of example here, I have a kind cluster set up, so that's Kubernetes in a local Docker, and I have a cluster that, so I have a PG cluster running here. If you look at the definition of the cluster, I have a, within my plugins, part of the specification, you can see there is a Barman Cloud plugin configured for this. And now if we go to the deployments, you can see that I have a Barman plugin deployment. So this would be the operator level plugin for Barman Cloud. But if I look at the pods of the cluster, you can see that there are 2 containers actually in the pod. And if I look at those containers, we can see one of them is Barman Cloud. So this is sort of highlighting how you kind of have your deployment at the operator level, but what it's actually doing is injecting an instance level plugin into my actual Postgres pod. Cool. So that is sort of the basic Barman Cloud example. And it's a relatively complicated plugin, but for our next thing, we're going to just show an example of an extremely simplified plugin just for fun demonstration purposes. So I'm going to walk through a MCP plugin for Cloud Postgres. This is just going to essentially implement a few interfaces, and it's going to attach an MCP server to all of my Postgres instances. We're going to be implementing only operator level plugins just for the sake of simplicity. We'll have an identity implementation. We'll have the operator lifecycle, which is what I'm going to use to attach my MCP server to my Postgres pod. And then we're going to have a reconciler, which is going to manage a new MCP service that I can connect to. We'll walk through deploying it and both the deployment of the MCP plugin as well as a service that allows that plugin to get discovered. Now, I have here linked below a very helpful project if anyone is curious, the CNPG-I Hello World project, which you can check out, and it has some really nice boilerplate for defining your own plugins, and you can use that. That is sort of the basis for this project. Now, let's walk through kind of each of these implementations. So this here is the generated Golang interface for the various interfaces that are associated with my gRPC definitions within CNPG-I. So as someone building a plugin, I'm going to be implementing these interfaces in order for CNPG to be able to execute the functionality I need. So in the case of the identity implementation, we're just specifying metadata associated with the plugin, as well as the capabilities of the plugin. So the plugin capabilities are going to specify to CNPG, that system, specifically what capabilities this plugin has and what it should be expecting to hook into. So things like the specific interfaces that this plugin is going to be offering. And then a probe to indicate the health of the plugin. Now, as far as those interfaces that we're going to be implementing, we have the operator lifecycle. This is going to be responsible for injecting into all of our Postgres pods a MCP server that we can utilize. Now, I will note that the MCP use case in terms of injecting it as a sidecar is not a requirement. You can, of course, run your MCP server as a deployment. But part of the motivation for doing it as a sidecar is that it is very consistent with the model that you would use for injecting a instance level plugin into your Postgres pod. So by injecting into the Postgres pod, we'll follow a very similar procedure. And even though we don't have an instance level plugin, we'll kind of show what that injection process looks like. And then finally, the reconciler implementation is going to be responsible for making sure we have a Kubernetes service that is created and managed as part of the cluster creation so that we can actually access that MCP server to talk to Postgres. All right. Now, let's actually look at the code. I have here this is the entry point. It's just and we have the definition of the gRPC server. You can see that I'm including an identity implementation, a lifecycle implementation, and a reconciler implementation. This is all based off of, this is provided with the help of this other project called CNPG-I Machinery. It has a lot of tooling and helpful features for building out these plugins. So CNPG-I is just the interface that you can implement in any language and any with any tooling you want. You just need a gRPC that implements those interfaces. But there's also some helpful tooling and things that you can use for building out your own plugins in Go, which is the standard Kubernetes way of doing it. If we look at the identity implementation, we can see that here are the functions that we needed to implement for this plugin. We have the metadata, which I can hop on over and see. We just have this Postgres MCP plugin name and then a bunch of additional information about my plugin. And then here's the important part, the plugin capabilities, which is going to define that this plugin specifically implements lifecycle and reconciler hooks. So when this plugin is running, the operator is going to know that I need to be calling this lifecycle and reconciler hook when I'm doing that work. So if we look at each of these implementations, we can see that within that lifecycle interface, we're actually specifying the specific lifecycle events that we want to hook into. And in the case of injecting this MCP server, we're going to hook into a create event. So anytime a Postgres pod is created by the operator, it'll call this lifecycle hook, and then also an evaluate event, which will be called anytime a pod is evaluated during the reconciliation process. And then as far as the actual hook implementation, we're just going to be, we can skip on down to the injection. So we're just objecting, this just injects into my pod spec a new MCP container that is going to be connected to my Postgres database. And it connects through a shared volume directly into the Postgres. So this is an advantage of running the MCP as a sidecar, is that it's able to connect directly to Postgres, the local Postgres connection. It doesn't need to use any service with special authentication. So this is the lifecycle implementation. If we jump over to the reconciler, again, we have the capabilities associated with this interface, and it's just going to hook into the cluster reconciliation. So anytime the CNPG operator is reconciling a cluster, it will be able to call this hook. It'll know that it needs to call this specific hook, which includes a pre-reconcile function that is going to actually ensure that there is an MCP service for my cluster. And if we look at what that looks like, it is just a simple kube service. So this is just going to be running and making sure that anytime my cluster is getting managed, I'm also adding a new MCP service that connects to my sidecar. All right, so that is the code associated with the plugin. And I'm going to go ahead and build that image and load it to my kind cluster. The last part of this is the customization for actually deploying. I'm using customize here. So this just is bundling my various elements of my plugin deployment. And the important ones to look at are the actual deployment YAML, which is my MCP plugin deployment, and then the service. The other stuff is related to TLS certificates that allow for the communication between the plugin and CNPG. If we look at the deployment, it's just a pretty standard deployment in Kubernetes. We can have the image is this image that I just built and deployed, and also the container port, which specify the place where my actual gRPC server that is serving these APIs is running. And then the service is what brings it all together. It is essentially what is configured to allow the CNPG operator to discover that this plugin is running in the environment and available for use. So I'm specifying as a label, this is the label that we talked about before, it is specifying the name of the plugin, and this is going to be used as a label selector on the CNPG. And then also, as annotations, you specify the plugin port in order to indicate to the CNPG operator exactly where it should go to connect to the service. And then the secrets for the TLS communication. So I'm going to go ahead and deploy this. I'm going to apply. Okay, so now my plugin should be running. If I go ahead and look at the deployments again, we can see the MCP plugin is running as a new deployment. We can see that there's also a service that the operator is going to be able to discover. But if I go and get pods, we can see that the pods only still have 2 containers. So the plugin, the new MCP server is not actually running on the pods, and the reason is we haven't added it plugin to the cluster spec. So I'm going to go ahead and edit the cluster to add into the plugin section this new plugin. So all right, so I'm just specifying the name of the plugin in the cluster spec. And now, if we think about what the expectation is here, now that that cluster has the plugin specified, it's going to cause a reconciliation loop that is going to be, it's going to notice that this plugin is specified in the cluster, and it's going to look up what registered plugins it has available. At that point, it's going to see that it's registered with the MCP plugin, and before the reconcile continues, it's going to hit that pre-reconcile loop, or that pre-reconcile hook in the external plugin that I have deployed. As part of that, it's going to create the MCP service. So if I look at the services, we can see PG Local MCP is a new service that was just created for my cluster. And now, once it's created the service, it's going through the reconciliation. The next part of is the lifecycle hook, which is going to mean as it's progressing and managing looking at the resources that it manages, one of those will be the pods for the Postgres cluster. And that is going to inject into as part of that pod evaluation, it will inject the MCP server into the cluster. So if I look at the pods, I can see I now have 3 containers running in the pod. And you can see the last container here is this Postgres MCP. So now my MCP server is running directly in my Postgres pod. And if I go ahead and port forward the port that I am exposing with that MCP service, let me go ahead and I have Claude set up here. I'm going to add a new MCP to my Claude and Claude model. So I have in my Postgres cluster, I have created a couple of tables and things already. So I'm going to try to query Claude to see a little bit about my database. So let's say my local Postgres schema and give index rex. So let's see if, so now it's going to use that local Postgres MCP automatically. It knows what to look for. It's connected as an MCP, and it's going to analyze the schema of my database and come up with some index recommendations. All right, so we can see that my database has departments and employees as tables, and now my MCP is giving me some index recommendations. So we kind of went through the whole process of basically creating, building this new plugin, deploying it, and then attaching it to my Postgres clusters. And now we have a fully running MCP server that is able to query my database and do operations on it. So that is the end of the demo. And there was now a lot of content that we went through in there. So I appreciate you hanging with me there. And yeah, there's a lot of power that you can have with these plugins. They can do a lot of different extensions on your existing Postgres database. So hopefully, if there's one thing that you can kind of take away, is just knowing that the capabilities are there, and if we can expand and make this the ecosystem of these CNPG plugins more extensible and more capable, that would be super exciting. So definitely think about CNPG-I the next time that you're looking at integrating a Postgres in your Kubernetes. Thank you.
If I can get the microphone working. Does anybody have any questions? We do have some time. Yes, 1 second.
If I wanted to run PG Bouncer with Cloud Native PG right now, how would that work? Is there a plugin for that, or is that built in?
So PG Bouncer, there is not currently a plugin for PG Bouncer. It's definitely something that you could implement a plugin for, but I also think PG Bouncer is something that could, generally speaking, exist outside as like an independent thing with just your Postgres connection. So if you have a reason or motivation to kind of tie your PG Bouncer directly more into like the life cycle of your cluster, you could definitely build it as a plugin, and that would definitely be a workable solution. But I do believe that there are some PG Bouncer implementations that you can also just run as like a separate deployment kind of thing. So yeah, it would definitely be possible.
Any other questions? Yeah.
You probably have mentioned, but could you explain again, like what is a plugin? Is there a one-to-one mapping from plugin to a Postgres extension?
So no, it is not a one-to-one mapping. It's kind of a separate thing. I think of sort of a plugin, like the CNPG-I plugin is to CNPG, or the Cloud Native Postgres operator, kind of what like an extension is to like your core Postgres. In terms of like you can have as it is just like a native to Kubernetes implementation of allowing you to hook into the whatever lifecycle or functionality is associated with Cloud Native PG, and you can have as many extensions within core Postgres as you want. You can add as many plugins as you want to the CNPG operator, but it kind of operates at like a one level of abstraction above like a Postgres extension. Because within CNPG, you can specify, you can configure extensions directly within that cluster manifest. You can kind of specify what you're going to be, the extensions your Postgres image is using. So it sort of operates at a higher level of abstraction. But yeah, it's kind of a similar notion though.
So if I want to add a plugin to my cluster, what does it look like? Do I need to like, will the cluster be restarted?
So it depends entirely on what your plugin is doing. So if you, in the example that we looked at today, right, where you're adding a plugin that is injecting a new sidecar, that is going to cause a pod restart, and that is something that you'd want to take into account. If you just created your cluster from scratch with that plugin, then that container is going to come up there. You're not going to have any issues there. But if you are adding a plugin that is injecting something into the pod, then you are going to have that behavior. It is going to cause a pod restart. But you can also have plugins that are just purely at the operator level, and they wouldn't touch the pod at all. It depends on what specifically your plugin is doing, whether or not it's going to cause any kind of restart. But yeah, there is no specific requirement that adding a plugin is going to cause your cluster to restart. It is entirely just because this particular plugin modified the pod.
Okay, but if I'm modifying the pod, and the cluster has more than one pod, like in the example you have like 3 instances. Would there be like a rolling restart or
Yeah,
fault
yeah.
over-
So is entirely managed within CNPG itself. So CNPG would make sure that if you have multiple pods, you have one primary and multiple replicas. And we didn't see it here in this example because all the pods came up relatively quickly, but it actually is going to execute a rolling restart. So it would first update the first, your replica pod to include the new container, while leaving your primary pod up and healthy. And then only once your replica pod is up and running with the new container, it would then do the restart on the remaining pod. So yeah, it will make sure CNPG is one of the core benefits of it is it will maintain uptime with your various pods as it's running.
Got it. Thank you.
Yeah.
All right. Any other questions? All right. Let's give Sharif another round of applause. Thank you so much.
Thank you.
All right. Up next is going to be the keynote in Ballroom D and E. You have a little bit of time before then, but thank you so much for coming.